Okay. All right, let's get started. So if you guys have the in-class thing that we did on Monday, get that out, because we're going to talk for the first little bit about what happened and see if any of you have any good ideas. So I will say at the outset, my goal right now is not to give you the answer yet. We'll circle back on all of these things and describe in more detail what's actually happening. But I'm just curious to know, does anybody that looked at experiment number 1, and just to kind of refresh your memories, experiment number 1, just some kind of simple diagrams here. That was one where you had a smooth ball, and as we increased velocity, the drag force went up, and then all of a sudden it started to go back down, and then it turned around and went up again, how we might expect. Did anybody that had looked at experiment number 1, does anybody have a satisfactory, to them at least, explanation as to why things did this? Okay, 1 second, David. Okay, so I think you should be on, David. If you want to unmute, people should be able to hear you. What's your explanation?
Sure. So my explanation for the first experiment was that in it's called the beginning region, when the drag force is increasing exponentially.
Yep, so this part right here.
Yes. So in that instance, the no slip condition around the ball is really slowing the air as it makes contact.
Okay.
And kind of similar to cavitation, when there's an obstacle in the way of flow, it causes the pressure to drop. And so it creates...
So where's the pressure high and where is it low? We're getting snow. Oh, my sadness. Sorry. You're probably not getting snow because you're in Florida.
It's 87 degrees outside right now.
We're all a little jealous. So where's the pressure high and where's the pressure high and where is it low in the, like, because you talked about having low pressure.
Yeah, so it would be high in front, I guess, where the flow is making direct contact with the ball, and then low behind the ball.
Like that?
Yes.
Okay, so then what's causing drag is the difference in the two pressures?
Where I made a conclusion about the second zone is that at some point you have a cavitation-like instance where the pressure becomes so low that the air is no longer sticking to the back surface of the ball, and it's not feeling the force of drag because there's just less molecules there. The pressure is so low.
Okay, so
if that makes sense.
Parts of it are not only make sense, they're, I would say, correct, and parts of it are not correct.
Yeah. Okay.
So you're right. Does anybody else have an explanation for why that part looks crazy? Nolan, you have an explanation?
Maybe it's when it switches from
laminar to turbulent. So I agree with that. I agree with what David said. I can hop back over here. Okay, so I agree with what David said. When David talked about the pressure on the front of the ball and the pressure on the back of the ball, he's absolutely right. The part that's wrong is that's always the case, and that's always going to be the part that's dominating drag force. So you can really have drag force from two so drag force can be caused because of pressure differences. It can also be caused because of fluid friction, right? Like tau equals mu du dy. So you can have drag force because of, it's snowing so much. Look at that. It's so distracting. Thought it was April. Okay, so drag force can be caused from pressure differences, and that's exactly what's happening in this case. The main component of the drag is the difference in pressure between the front and the back. The shear stress, everybody's just looking out the window. The shear stress is only like a little portion of the drag force in this. So the like fluid friction isn't actually a big part of it. What's happening is really, as David described, this pressure difference on one side of the ball and the other. And like Nolan said, right here, we go from laminar to turbulent. So that's our laminar to turbulent transition. And that's why you get kind of goofy, like it flip-flops a little bit, and you get this really goofy behavior because you're switching from one flow pattern where things are laminar to a different flow pattern where things are turbulent. And for some reason that we'll get to later, that causes this decrease in pressure drag. So the pressure on the front and the back of the ball become more similar when we switch from laminar to turbulent. Again, we'll explain why later. Experiment number 2. Maybe I just helped you a little bit to explain that. But if you're somebody that did experiment number 2, I would imagine, right, this is the one where we saw like a rough ball versus a smooth ball. And at some velocities, the rough ball had a factor of 5 lower drag than the smooth ball, which is super surprising, at least to me. Oh, was it surprising? They're like the same ball. Almost nothing is different, and you get a factor of 5 difference in the drag force. So did anybody who did experiment 2 have a reasonable explanation for that? Yeah, Brett?
I thought of it as like a golf ball. It makes like turbulent flow kind of over the surface of it. And then that in turn kind of decreases the size of like the air pocket from that ball.
Yeah, so you're exactly right. And so you can think about this similar to why a golf ball is shaped like a golf ball. So a golf ball intentionally is not smooth. You buy it brand new and it's got bumps on it. And that makes it fly farther, which again, when you stop and think about it, you go, that doesn't seem to make sense. Shouldn't a smooth golf ball, which doesn't have as many bumps, have less friction and be able to fly farther? Usually smooth things are better. And the answer is, of course, no, golf balls are designed that way because it's better. When people first started golfing, they thought, as you might, a smooth ball should fly farther. So they made their golf ball smooth. And then as you kept playing with the same golf ball, once it got old and ugly and kind of looking like garbage, then it worked a lot better. So that's why people like started intentionally taking golf balls and, you know, making marks in them and cutting them up because they realized my old golf ball that I hit into 4 trees works better than my brand new golf ball. It flies way farther. I don't care what's going on. Let me just scuff this one up and we'll see what happens. And then people finally started to actually, okay, we'll design new golf balls to be bumpy and funny looking. So you get kind of what you're getting at with the kind of this air pocket, I think is the term that you used, that's behind there. there's truth in that. But yeah, with the rough ball, you kind of induce turbulence. And maybe one way to think about it is you go from where the smooth ball is still stuck kind of on, the smooth ball is still stuck maybe up here. The rough ball, you get to jump ahead and kind of get onto this part of the curve down there. You get to jump from the laminar curve down to the turbulent curve, kind of before it was time to. And again, we'll talk about exactly the physics of that and why that works. Problem number 3, why are fish shaped? Anybody ever thought of that? Right, every fish that you've ever seen is designed to cut through the water and be as water dynamic as possible, to be able to cut through the water as easily as possible. And all of them have like basically a blunt face, and they're long and pointy on the back end. So why does that shape cut through the water? Why aren't they like long and pointy on the front end, and it doesn't matter what happens on the back end? Because you're trying to cut through the water, aren't you? The answer is, of course, like fish are fish shaped because that's the best shape. Right? You haven't thought about this, have you? Like, so, okay, so bomb versus the ball. Why does the bomb shape work better in some conditions and work worse in other conditions? Right? We had in air, it was always better. And glycerin, which is like a really viscous, sticky fluid, then the ball shape was better. For fish, it must be like water's kind of more like air. It's not quite as viscous as glycerin. Otherwise, fish would be ball shaped. They'd like swim around looking like pufferfish all the time. But they don't, so they're bomb shaped because that's a better shape. Did anybody that looked at experiment 3 have an explanation for that? I know people looked at it. Otherwise, I'll make you raise your hand if you looked at experiment 3, and then I'll just call on somebody. Wrong explanations are accepted. It's okay to be wrong, especially when you are supposed to be trying to figure something out and you haven't learned it and you're trying to think about it. Barry?
Is it because the tail makes it harder for like a turbulent patch to form behind the ball and like sort of suck it back?
That's exactly right. So if we think about, it's talking about the long extended tail, the long pointy part on the back, that makes it harder for this kind of low pressure air pocket, whatever we want to call it, to form behind the shape. If we think about what's happening kind of in the context of the video that we watched before, where we looked at pressure and flow and looked at what happens to fluid boundary layers, maybe we can start to think a little bit better about this. So we have high pressure kind of at the front end because the fluid's going to come in and crash into that front end and slow down. And as velocity goes down, pressure goes up. As you go, so that's true, you're coming kind of down this way. Then you curve and go around the corners. When you get to that edge, that's where you're moving the fastest. So your pressure is the lowest. And then as you move around the shape, pressure has to go back up. So you're moving from here, you're moving against pressure. So we'll call this P medium high down here. So you're going from low pressure to like medium high pressure as you go around that corner. And you get kind of a long time because it's a long, slow point. The pressure change isn't super fast. So you can kind of keep moving around the shape before you come off and form like a wake. So you kind of keep moving and then eventually you kind of get unstuck from the surface. But you have a relatively small wake because that pressure rise is slow. For a ball, you get the same 3 pressure points, but you come around here and then the curve is so sharp, you basically just go like this. And you get this huge wake around the object. And that wake gives you high pressure on the front and low pressure on the back. And that's what's slowing your ball down, or that's what's giving you more drag. Why doesn't that happen in the glycerin? In the glycerin, it doesn't happen because velocities are low and viscosity is high. So in both cases, you'd like get stuck to the ball surface around the whole ball. And then what's happening is fluid, like friction, is what's dominating. And the ball has small surface area and the bomb shape is big surface area. So friction matters more. This pressure stuff doesn't matter because velocity is low. So like I said, we'll dig more into the aerodynamics of drag. This is certainly not the last word, but what I wanted you to see with these initial examples is it can be easy when approaching fluids, especially if you know a little bit, to like look at something and say, oh, I know how that's going to work, and be super duper wrong. And that's true, like, obviously of people like you that are brand new to fluids, but even, you know, if you have a lot of experience in fluids, if you're approaching a new problem, just kind of guessing what the physics are going to be is always a little bit dangerous. So you kind of have to calibrate yourself with experiment. Right? So if you want to design something, you kind of use the expertise, use your experience to be able to design it, but then you're also going to be calibrating that to experiment. And you guys all know that this is true about fluids because you've seen like videos from car commercials about testing the aerodynamics of a full-size car in a wind tunnel. If you could get all of the information about automobile aerodynamics from a computer simulation, I can promise you it would be cheaper to buy a computer than to build a whole huge wind tunnel. So we do wind tunnel experiments because you can't get all of the information about your car's performance from just a computer simulation. Something like a car, though, is, I guess, it's relatively easy. What if you're trying to look at a 2,000-foot skyscraper and you want to look at wind forces on that? Do you really want to build a wind tunnel to fit your 2,000-foot skyscraper in and test it on a full-size scale model? It's cost prohibitive. What about, like, so let's say, okay, we're not going to build a 2,000-foot model. Let's build a 2-meter model or whatever. Let's build it smaller. How are you sure that what's happening in your scale model is the same as what's happening in your 2,000-foot building? They're super different. Like, do you use just like a different wind speed? How do you connect the two? Okay, different example. What if you tried to use, so we'll call this part like how do we design experiments? So say we wanted to get an idea of like wind forces on a model building. How do we design an experiment that we can actually figure that out? What if we wanted to look at drag forces on an ocean liner. Okay, it's going to be, again, cost prohibitive to build that and then like try different hull shapes at scale for like 1,000-foot boat. So what if instead of 1,000-foot, what if we made like a 1/10 scale model? So let's say we have drag forces an ocean liner moving, say, at 30 miles per hour. And we use we'll say a 1/30th. So we want to use a 1/30th scale model because then it's a reasonable size. We can build it and we can maybe do some iteration on that. What speed should we push that through the water? The 30th scale model, if we do it at 1 mile per hour instead of 30, does that work? Can we do that? Maybe? Or do we use like 8 miles per hour? Or do we like use a fluid that has a different viscosity than water? And we did like 4 miles per hour in ethanol, which has a different viscosity. Like, I don't know, what do we do? How do we, so the real question, kind of underpinning things like this, is how do we match the physics that's happening in our experiment to the physics that we expect in the real world? Just the last example, because this is from just the other day. So have people seen this video? Hopefully some of you have. This is on Mars. It happened the other day. This is a little helicopter. You can kind of see it down there in the bottom middle. So again, presumably the engineers that designed this at NASA had tested it and knew that it was actually going to fly on Mars before they sent it to Mars, because otherwise that's kind of an expensive experiment. So if you don't know that it's going to work, you can't like send it to Mars and convince people to put it there and then be like, oh, sorry, we thought it was going to work. I guess it didn't. But no, they had tested it. They knew that it was going to work, and they sent it to Mars, and there was no damage. Things were fine. You can make a helicopter that flies on Mars. But where would you test that here on Earth? Earth has a different gravity than Mars. Earth has a really different atmospheric pressure. So you can't just like take a drone that flies here on Earth, send it to Mars, and expect that to work. What's happening is going to be super different. So there are some experiments where we can just do the full scale experiment, and that's easy, and we can iterate with it, and everything is fairly straightforward. If you're trying to do like the aerodynamics of a bike helmet, you could probably just make a full size, like a couple different bike helmets that are all full size and do your experiments, and it's fairly straightforward. If you're trying to do a helicopter on Mars, you can't like iterate that. You have to iterate it here on Earth in different conditions before you send it to the conditions that it's actually going to perform in. If you're trying to develop an ocean liner, you can't really iterate on that at full scale. You have to do small scale stuff and then be able to somehow connect what's happening in the small scale to that super large scale. So the question is kind of, how do we know what's important, and I guess like how important those different parameters are? So again, if we imagine looking at, let's say, a skyscraper. So here's our skyscraper, and we want to look at wind blowing against that skyscraper to make sure it doesn't blow over. generally a good thing to do. We have wind blowing at some velocity. So one way that we could do that is kind of test a whole bunch of different conditions and like change all of the variables and then see how changing each individual variable changes the forces acting on our building. So we could look at forces by changing all the important variables. Okay, so what variables are going to potentially be important in a situation like this wind blowing against the building? This again, so we're thinking about like what important variables for our model system. So one is going to be the size of the model. So we have to know how, like, using a model that's twice as big, what effects does that have on the forces? Is it just going to be like a straight doubling, or is it going to be something different? So maybe we want to take not just like one set of like data at one size and data at another size. Maybe we want to get like a couple different sizes. So we'll take, I don't know, maybe like 10 as a reasonably small number. And we'll say if we do 10 sizes, we can probably then understand how size translates, like how different sizes behave differently. So let's say we did 10 size models. Okay, we can make 10 models. Okay, not going to be that hard. What other parameters are going to maybe be important? Velocity is probably going to be important. So for each of our 10 models, let's use different velocities and then be able to measure that, and we'll be able to figure out how velocity impacts things. So we'll do 10 models, 10 wind speeds. But probably the properties of the fluid are going to matter too. So things like density and viscosity. So we should probably do those too. So 10 fluid densities. Okay, that one's maybe a little bit trickier. How do we change the fluid density? We could use different pressures. Or maybe different fluids. We use two different fluids, like a liquid and a gas, or two different gases or different liquids. We could change density. And then we should probably use 10 fluid viscosities. Again, just because that's going to be like how much viscosity there is, that's going to be what's going to matter, and how much shear stress there is, and also kind of how the fluid is behaving. So we probably would need to do different temperatures or different fluids to be able to look at different viscosities. And by the time we're done, we did at each of our 10 models, we do 10 different wind speeds with 10 different densities and 10 different viscosities. That's 10 times 10 times 10 times 10. And very quickly, we're doing 10,000 experiments to be able to characterize our model. Each experiment, I don't know, you hire a couple interns, they can do 5 experiments a day. So it's going to take a while, like, I don't know, 5 years, 4 years. And then you'll have done all the experiments, and then you can go look at your data and figure out how each of these things matter. Clearly not the most efficient way to go about doing things. So what we really want to do is design a smaller number of good experiments. You don't want to do every experiment. You want to do the smallest number because you don't want to do extra work. Okay, you want to hire your intern to do a smaller number, so then you have to hire less interns. But you want to do that so that it doesn't take forever. You can get all of the information that you need without having to do everything. So this is kind of what we're going to be trying to do. And we'll do this by looking at the physics. So we're going to pick good experiments looking at the physics of what's going on. So what I mean by that is we want to be able to tell, again, if you go back to, say, this first experiment, we want to be able to tell, like, are we on this curve? And if so, where? Or are we somewhere in the middle here in this where like goofy things are happening? Or are we somewhere over here where different things are happening? Like, where do we actually sit in terms of the physics that's going on? Because only through that can we actually be able to figure out like how we can start to compare what's happening in our model system to what's happening in the real system. If we take a model system and we are, for example, like in our model system, I just killed it. Okay, if in our model system we're over here, the conditions that we pick for our model, in our real system we're over on this other side, insights that we gain from our model are going to be totally meaningless for our real system because the physics is different. So we have to make sure we choose stuff that matches between the real system and the model. So we do that by looking at the physics. Okay, so for the physics, how do we know what's important? Well, we can look, we don't have to necessarily solve the equation. We just have to look at what are the kind of key parts and what are the key groups of things, or what are the key sets of variables that we have to do experiments around. So we'll do that by looking at, say, for example, we want to look at drag force on a building, or wind force on a building. That's going to be governed by the fluid motion, really by the continuity equation, conservation of mass. And it's going to be governed by the Navier-Stokes equation, F equals ma. So we're going to have continuity. Which would be du dx plus dv dy equals 0. And Navier-Stokes. Navier-Stokes, they're going to be potentially like multiple different dimensions that are important. So maybe the x dimension and the y dimension, and the z dimension, again, generally, but we'll just look at x and y for right now. So in the x direction, this would be rho du dx plus v du dy plus, equals minus dp dx plus mu d squared u dx squared plus d squared u dy squared. Okay, and you can see in this equation, all of the parameters that we said were important show up in the equation. Okay, density is important, so we see a density show up in the equation. once we get that back. So we see, okay, density shows up right there. Viscosity is important. Viscosity shows up right there. Size is important. We see like X's and Y's show up there. Velocities are important. We see U and V, U show up in the equation. So the important parameters are the things that show up like in the physics. Those are the things that are important. Okay, pressure, that was one thing we didn't actually look at, but pressure might also be important. We see a P show up there. Okay, so let's do 10 more experiments at 10 different pressures. All right, things can very quickly get lots of fun. What we're going to do is try to simplify this down and condense it down so that we don't have all of these separate things. And we're going to do that by non-dimensionalizing. Before we do that, though, let's look at, okay, so that's the X. This would be the Y direction. And we'll look at this because this will have, it would be very similar. Sorry, this is that's a U dV dx plus V dV dy. Because the Y dimension maybe has gravity in it too, for example. So rho G minus dP dy plus mu d squared V dx squared plus d squared V dy squared. Okay. So our goal they depend on boundary conditions. And a small number of parameters. So instead of all these different things, let's boil it down, condense it down so we get, okay, the solution is still going to depend on the boundary conditions or like the shape. So if you want to look at the building, your scale model has to match the full scale model in terms of what it looks like and the shape, but then also the whatever the important parameters happen to be. So we do that by non-dimensionalizing the problem. So we use non-dimensional variables. Again, just as like, this is the same thing. If you're not familiar with non-dimensional variables, this would be like saying, I'm 1/3 of the way home. So you have like 0, you have your house, and you have U there. So this is L, and you're 1/3 of the way to L. So you would do this by saying like your position on your way home is X. Your non-dimensional position is your actual position divided by the total distance. Like, say it's 3 miles home, you're a mile into your trip. A mile divided by 3 miles is 1/3, so you're 1/3 of the way home. So we're going to use the same basic strategies, or you could say the same kind of things for velocities. You could say something like I run 0.26 times as fast as Usain Bolt. So you can compare your speed, that's my top speed, You could compare it in like, what is human speeds? You can compare it to Usain Bolt and say, I'm this % of the way to Usain Bolt's speed. So you take your speed of, I don't know, like 8 miles an hour divided by Usain Bolt, who's like 32. Super fast. Probably get a little bit faster than 0.26, but get the picture. So you can compare it, and you can do this with other things too. We're going to do the same thing with like non-dimensional pressures and gravities and all kinds of different things, but you're trying to get like kind of scale it to the system. It is snowing so much. It's amazing. It's like winter out there. I'm jealous of David's 87 degrees. Okay, so our non-dimensional variables, if we took the continuity equation and the Navier-Stokes equations, we're going to have kind of non-dimensional versions of all of the variables in our problem. So we're going to get like x star is x divided by some distance. Y star is your current y position divided by a distance. And then you get the same like velocities. U star is the velocity divided by some reference velocity. V star is little v divided by that reference velocity. And you can get like non-dimensional pressures. It's the pressure divided by rho. That's supposed to be a v squared. So sometimes the non-dimensional group is really straightforward, like position over the side. Like you can kind of just guess what that would be. Sometimes it's like the pressure one where it's a little bit more, it's not super clear. So we'll look next time at different ways to kind of figure out what those groups of variables or how we would non-dimensionalize it. But if we do that and we looked at, say, the y direction Navier-Stokes, non-dimensional, it would look like this. U star, dv star, dx star, plus v star, dv star, and y star equals minus g L over v squared minus dp star dy star plus mu over rho v L d squared b star dx star squared plus dy star squared. So you can look at, again, this would be describing the physics in a non-dimensional way. And the reason that we would do this is, blue. This right-hand side is that's the fluid acceleration, right? Navier-Stokes is trying to say like F equals ma. That's the A part of it, acceleration, talking about fluid movement. This side are all the different forces that are in the system. And we can look and use kind of, so how do we know if gravity is important? Well, gravity is not important if G is big, because gravity is like the same size. But gravity is important if this collection of variables is big. So we don't have to do, like gravity is not like its own thing, kind of living in its own land by itself. It's this whole group of things. And gravity, when like that group of things is, say, 10, is going to be the same when that group of things is 10 versus like another system where maybe the individual values change, but the whole group is still a value of 10. The physics are going to look the same. So this is, just for example, this is a lot of these things have fun names. We'll look at some more of them, but this would be the Froude number. Which is like a non-dimensional gravity. So if the Froude number is itsy bitsy teeny tiny, gravity doesn't matter. If the Froude number is really big, then it does matter. If the Froude number is the same between like system A and system B, then the effects of gravity are the same. The results of gravity are the same in system A and system B because it's the same number. This is obviously pressure. This last term is from viscosity. And you can see obviously right there, that's 1 over the Reynolds number. So what we're going to eventually do is say, like, okay, if we want to match the physics, say in a system that gravity matters and velocity, like fluid motion matters, then we would say, okay, we're going to match the Reynolds numbers, if those are the same, and the Froude numbers are the same, if gravity is working the same, and the fluid motion, viscosity effects, those are working the same, then the physics of our real system and the physics of our model system will match. And something that happens, say, like 50% of the way down our model is going to happen 50% of the way down our real thing. We'll be able to take information that we get, say, on our model system about drag or some other effect and translate that directly from our model into our full-size system. So we'll look at this in a little bit more thorough, systematic way next time, but we'll start to kind of look at this in terms of how we can translate from model systems up in scale or to different, maybe systems that we can't measure in experiments. So we'll end there. The only thing that's going on the rest of the week till Monday in fluids is the design project. So feel free to shoot me an email if you have a question on that, that I can help clarify, or come and find me or something like that. But yeah, keep plugging away on the design project. Yeah.